Welcome back to PDEs. We're going to continue looking at Laplace's equation, this time on a circular boundary. This problem in particular has a Dirichlet boundary condition. I probably butchered the pronunciation of that word, but non-derivative boundary condition. So Laplace's equation looks like this. GURR, partial derivative, second partial derivative with respect to r, plus 1 over r ur plus 1 over r squared u theta theta equals 0. So what we're looking at here, of course, this is a circle, so we're looking at polar coordinates. Which consist of r, the radius, and theta, the angle of the positioning on the circle. So it wants us to find the solution u of r theta of Laplace's equation. On the outside of the circle, r equals a, so the radius of the circle is a when theta is between 0 and 2 pi, so it's a full circle. Here's theta, between 0 and 2 pi, so that means theta is periodic over 2 pi. Solution is periodic over 2 pi. On the outside of the circle, that's satisfying the boundary condition, UA of theta equals F of theta. So the entire, so this is what's in black is the boundary that condition is for, F of theta. This whole black circle is F of theta. It wants us to find the solution out here. So everything out here is r at some distance r at some theta. You know, it can go all the way out to here. It wants to find that solution. It tells us that assume UR theta is single valued and bounded for r greater than a. Let me just mark this up here. So, don't be intimidated by the more complicated looking equation. It's not too bad. But as we know, for any PDE, step 1 is separating the variables. So, remember, we define u r theta. This is just like any other PDE as being theta. Actually, let's do r of r, theta of theta. That's a capital theta. It's like a circle with an h in the middle. From that, we can solve for urr, which is r double prime theta. Ur would be r prime theta. U theta theta would be r theta double prime. So let's plug those into our equation. R double prime theta plus 1 over r prime theta plus 1 over r squared u theta theta, which is r theta double prime, is equal to 0. So let's separate the variables. We want to divide the whole thing by r theta in order to separate the r's from the thetas. So this leaves us with r double prime over r plus 1 over r times r prime over r plus 1 over r squared times theta double prime over theta equals 0. Let's go ahead and multiply the whole thing. Let's get rid of the fractions, multiply the whole thing by r squared. I'm doing this for a reason. We want the radiuses to be with the radiuses. So let's go ahead and get those with the r's. So let's go ahead and multiply by r squared. That leaves us with r squared, r double prime over r, plus 1 over r. No, that cancels. Plus r prime over r. I'm going to introduce the separation constant and move this over. Like so. Remember, the r squared cancels. We can now write our two equations. So this leaves us with r squared, r double prime over r, plus r prime. Actually, let's multiply the whole thing by r. And I'm going to move this over, so it's going to be minus lambda r equals 0. This other one, let's multiply the whole thing by theta. So multiply lambda by theta. We're going to move this term over to here. So that becomes positive theta double prime plus lambda theta equals 0. So these are the two second order linear homogeneous, probably spelled that wrong, ODEs. Step number 2, as we all know, solve the boundary value problem. Now, you're thinking, what in the world, how are we going to do this? We're not given any, we have one boundary condition here that tells us this f of theta value, but we need to use that for a Fourier series, right? We can't use that now. So what do we know about our boundary so far? Well, we know at the boundary the radius is a, okay. We also know that that doesn't really help us though, because it doesn't tell us where we are on the boundary. What tells us where we are is theta. We know the distance to get to there is a, but in order to tell us where on the boundary we are, we need theta. So we're going to use this equation for a boundary value problem. And the reason why is because we also know theta is between 0 and 2 pi. And so that tells us that this is a full circle, and because it's a full circle, theta has to be periodic with 2 pi. Okay? So we know that theta has to be periodic with 2 pi, right? Think about it. The solution here is the same as the solution here. Solution here, same as the solution here. Solution here, same as this. I'm sorry. But you know what I mean. It's periodic with 2 pi. If you're here, if you add theta to it, it has to go around back to here. Same solution. So it has to be periodic with 2 pi. So a better way of explaining it, I don't know why I did this whole thing. I mean, if you're starting from the center and working your way out, yes, the solution would be the same here and here. But that doesn't have anything to do with periodicity. I don't know how to pronounce that. Periodicity. But if you're here and you make a full revolution, you're going to end up at the same solution. That's all this is saying. If you start here, you go around, end up at the same solution, no matter where you are on the circle. End up at the same solution. So we know theta has to be periodic with 2 pi. That means that theta has to be periodic with 2 pi. This allows us to define that theta of theta is equal to theta. Same solution as if we have theta plus 2 pi, right? So we're going to solve our boundary value problem just like we've been. Let's look at case 1 when it's greater than 0. When lambda is greater than 0. That defines as being positive mu squared, because it always is positive. If this is the case, our equation becomes so this is going to be complex when we solve the characteristic equation. Leading to the general solution of C1 cosine. Right, this is the shortcut for Euler's equation. C2 sine of mu theta. Looking at this, we can just look at it and we know that for theta here, this is period. Cosine and sine are naturally periodic functions, but in order to maintain that, mu has to be in either constant negative n or constant positive n to maintain periodic. So mu has to be, let me do this in orange. Mu has to be negative n or n to maintain, oh boy, period. I've definitely, you know what I mean by periodicity. I'm probably butchering it, but mu has to be negative n or n to maintain it to be periodic. So, but looking at this problem, we know that lambda has to be a positive mu squared. So no matter what we make mu, it's always going to be positive. So because, I'll say this. But lambda is equal to mu squared. So no matter what, lambda is always going to be equal to negative n squared, which is always positive. So mu has to be positive n for theta to be positive. So that tells us that lambda, so let's write out our things here. We know lambda n has to be equal to n squared. So then theta n is equal to C1 cosine n theta. I'm actually going to use an and bn because we're using n now. Sine of n theta for every n is 1, 2, 3, and so on. So this is pretty cool the way this worked out, right? You can kind of see how it works. Put this in the middle, it's bothering me. Okay. So that's case 1. Let's look at case 2. Oh, let me erase this. I was doing it on myself before. We'll get to there. Case 2. Lambda is equal to 0. If lambda is equal to 0, look at our formula. Theta double prime equals 0. So then theta is equal to C1 plus C2 theta. Right, because I know this is r squared is equal to this is r is equal to plus minus 0, which is repeated roots, so they use the shortcut to reduction of order. Looking at this, we know that theta has to be constant. If it's at one location, it needs to be the same when it makes a full revolution. It cannot change. It needs to be the same. It needs to be a constant. So in order for that to happen, so my assumption, I'm going to write this down. My assumption is that C2 has to equal 0 to maintain theta over 2 pi. We can test this theory. Remember, we find that theta of theta is equal to theta of theta plus 2 pi. So theta of theta is equal to theta of theta plus 2 pi, which is going to look like this. So this is the proof. So that's C1 plus C2 theta is equal to C1 plus C2 theta plus C2, well, 2 pi C2. I'll call this theta C2. So let's look at this. How can this here, well, how can this here technically be equal to this here? Well, only thing that's off is this term right here. So as we can see, has to be 0 for this, right? So theta, so then our lambda n is 0 for this case. Our theta n is equal to C1, which this is for 0, right? So this is 0, 0. This is for n equals 0. All right, so we have our two solutions so far. Right, the reason it's n equals 0 because this part of the solution defines that it's constant throughout, no matter what value n you're on. So it's always going to be added on to the summation. So it's constant. That's why n is 0. We have case 3 now, where lambda is less than 0. If lambda is less than 0, it's equal to negative mu squared. So we have theta double prime is equal to negative, becomes positive, mu squared theta, or does it? Yes. So then solve the characteristic. Come up to here, write this out. Theta n equals C1 e to the n theta, no, not n, mu theta, plus C2 e to the negative mu theta. That's a theta, by the way. That's a mu. I used to be very good at writing mu's. Now I can't. Okay. So that's this. Now let's take a look. Obviously, this is not by definition periodic, so this is kind of like the same case as last time. We need theta to be constant on both sides as it makes a revolution around. It needs to stay the same. can't change. So in order for that to happen, I can see that this here and this here should be equal to 1. So my assumption is that mu equals 1 to maintain constant periodicity. So then theta n is going to be equal to C1. Well, let's do our little proof again. I'm getting ahead of myself. Theta of theta is equal to theta of theta plus 2 pi. This becomes C1 e to the lambda theta plus C2 e to the negative, mu theta, not lambda, is equal to C1, C1 e to the mu theta, mu theta plus 2 pi plus C2 e to the mu times theta plus 2 pi. That's negative. This can be rewritten as, let me copy this. This can be rewritten as C1 e to the mu theta times, you just multiply these together, mu times 2 pi, so that make that 2 pi mu, plus C2 e to the negative mu theta plus e to the negative 2 pi mu. So now let's take a look. What would make this equal this? Well, if let's take a look. What terms do we want? We want this term. That's not plus. We want this term, and we want this term. They're only going to be equal if this is equal to 1 and this is equal to 1. So this has to be 1, this has to be 1. Let me not do that in green, it's kind of hard to see. Have to be 1. So that tells us, in order for that to be 1, mu has to be equal to 0. Right? So because mu is 0, that is less than 0. Lambda is less than 0. This case is never periodic. So this solution does not work. So this led us nowhere. So we have our solution so far. We have the lambda equals 0 case, and we have the lambda equals n squared case. So let's continue on. I need more pages. Whoops. So what we need now is the next step, step 3, which is solving for the other variable. In this case, it is r. What was the formula for r again? Oh, is that long? I remember what it is. It is r squared r double prime plus r prime, because it follows the formula for an Euler equation. That's how I remember it. Minus lambda r equals 0. So this, if you remember back to second order ODEs, is an Euler equation. So if you remember, for an Euler equation, we had to propose r equals r to the h. I'm going to use, I remember we used different values before, but it's the same idea. I'm going to use h's instead of, because I think it used to be something to the r. So then r prime is equal to hr to the h minus 1. R double prime is equal to h times h minus 1 to the r to the h minus 2. Remember this from second order? So then we plug all these in here. We get r squared h times h minus 1 times r to h minus 2 plus r h minus 1 minus lambda rh equals 0. Let's see here. Let's go ahead and do this. Multiply this through. Plus r negative 1 minus lambda rh equals 0. So as you can see, this cancels with this. This cancels with this. Sorry, this too. Come on. Thank you. And we're just left with the the RH. Wait. Oh, because we can take out the RH. So hold on. This is h squared minus h plus h minus lambda equals 0, because I pulled out the RH. See, that's just, we ignore because it's going to equal 0. So we're left with this. This becomes h squared minus lambda equals 0. So now that we are here, this is the point in which we need, before we take the square root, we have to plug in lambda first. So we have two cases for lambda, right? We had n squared case. So let's look at this again. If this is equal to n squared, we will be left with where h is equal to plus minus n. So then r is equal to c1 r to the n plus c2 r to the negative n. And this is where things get weird. So this is interesting because, as you know, for this particular case, we defined that n always had to be positive n. Well, if you think about it in terms of a circle. So, first of all, these should be n's. This should be a sub n, b sub n. So, think about it in terms of a circle. Whenever you have something like this, think about it in terms of limits even. If we're decreasing, so we have the center of the circle, right? This is the radius. What if we're going towards 0? What if the radius is decreasing? Means this bottom is increasing. If this is decreasing, this whole term is increasing. Exponentially, as n increases, this term goes to infinity. This happens as r goes to 0, right? Whole term is going to increase as r goes to 0. And now if this were to be going, if this r value were to be increasing, the whole term would shrink, right? But now let's look at the other term quick. As n increases, this term goes to infinity as r increases. Well, as r goes to infinity. And we know that for the exterior problem, when r is greater than a, we need to be bounded at infinity, where we need to get value at infinity. So this term right here has to be discarded. This is the only term here that's going to go to a value as r increases, right? If r increases, this is going to go to 0, which is bounded, if that makes sense. I kind of explained that poorly, but another way of writing this is as n increases, this term goes to infinity as r goes to 0 as r goes to infinity. It's bounded, right? So as it goes to infinity. So we only use this one term. So create a little box. R to the n is b sub n, r to the negative n. Now, next case, lambda 0 is equal to 0. So for this case, we're going to have r squared, r double prime, plus r prime. Lambda is 0, this is equal to 0. So we have to solve this problem here. So let's reduce the order. So let's set v equal to r prime, v prime equal to r double prime. This leaves us with r v prime plus v equals 0. So then we can separate the variables. dv dr equals negative v over r, right? That's what dv is, dv dr. Separate the variables. I'm going to bring this negative over to here. Actually, I'm just going to keep it there. Yeah, move the v over, move the dr over, integrate both sides. Natural log of v is equal to the natural log 1 over r plus c. We know that v is equal to c over r. Oh wait, well that's what you get. That's what we get from taking the exponential of these, right? E both sides. This is e to the ln of 1 over r. That's just 1 over r times c. So it's c times 1 over r. V is equal to r prime. Integrate. This becomes dr. I'm going to move the little dr over. R integrate. R is equal to c natural log of r plus c1, or just plus c. Now, taking a look at this, we can see that as this term, as r increases, the natural log of r goes to infinity. So this term we ignore. So the r naught is equal to c naught in the end here. So for this case, we have this. So now the hard part of this problem is over. Now it's just writing out fundamental set of solutions, the general solution. So for the fundamental set of solutions, we're going to have u of 0 r theta is equal to a naught. I'm going to call it that instead of, because this is c naught times y naught. I'm sorry, theta naught. Where's theta naught? It's c naught. So it's c naught times c naught. I'm just going to call it a new constant, a naught. And then we're going to have un of r theta. This is equal to theta n times rn. So theta n was, right, cosine plus sine and theta. What is r0? I mean rn. R to the negative n. So that'll be, we'll call this, I'll just write it out first. This should be negative n. Sine is b to the n. Sine and theta. Where u r theta is a naught over 2 plus n equals 1 to infinity of a sub n. I'm multiplying them together now. C to the n times a sub n is going to be equal to a sub n. R to the n. I'm doing this for a reason, so we get the standard Fourier coefficient notation. This should be negative n, sorry. And theta. Right? Makes perfect sense. I need another page quick. This is our general solution. We superimpose the fundamental set of solutions to get to the general solution. Okay. General solution. Now, let's use the boundary condition to solve Fourier series, step 5. So we're going to have u of a theta, I think that's what they gave us, equals f theta. That's right on the boundary, right on the circle. That's equal to, remember, I forgot to tell you, the reason I divided this by 2 is just by normal convention, right? That 2 didn't just come out of nowhere. Watch my Fourier series coefficient derivations, and you'll see where that divided by 2 comes from. But let's continue here. We're plugging in A for R. Right? So in this case, A sub naught would be equal to 1 over pi. Think about it, because it's the length, which is half of the period. Period's 2 pi. So the length is pi. This is going from over one length. Actually, no, it is 2 pi. But it's 2 over... Yeah. So we want to extend it into the other frame. So we're going to multiply it by 2, go from 0 to 2 pi. And then we have f of theta, d theta. Right? So now a sub n, we're going to multiply it by a to the negative n is equal to 2 over 2 pi, 0 to 2 pi, f theta cosine n pi, d theta. Actually, no, wait, sorry. This is n theta, d theta. And then we have b sub n times a to the negative n is equal to 2 over 2 pi integral 0 to 2 pi f theta sine n theta d theta. And this is our coefficients, which get plugged right into our general solution up here. Right? So that's the answer right there. If we were given an f of theta, obviously we could integrate and then plug in, but we are not for this problem. But you can see this is definitely a different solution than what we've been doing in PDEs. We have to focus a little bit more on theory rather than pure mathematics, because we have to think about how circles work, right? But anyways, hope you enjoyed. In the next video, we're going to look at a semicircular region. And then, which is a little different. And then we have another full circle, but on the inside, I think. Yes, on the inside of the circle, and it's a Newman problem. So we have a semicircle and then a Newman problem. So I hope you enjoyed this video, and I'll see you next time.